Connecting to cloud server. Okay, good. Okay, so welcome everybody to our seminar. We are continuing in this good environment and good company. And today we have Reinier Diaz Millan as a speaker. He joined Australia relatively recently from Brazil to strengthen our optimization community. And we do hope that he will do it well, and we already see that this is already happening. So first, welcome Reinier to this island. And I hope you will not regret your move to this community. And we do need your experience in optimization and everything around. So Reinier is going to talk about optimization. He's presenting some new algorithm related to rational approximation. Although I guess this is just an illustration for his algorithm. So please, Reinier, the floor is yours.
Okay, thank you. Thank you, Alex. Thank you everyone for being here. And thank you, the organizer, for inviting me to this talk. My talk is, I will present an algorithm for solve pseudo-monotone variational inequalities with application to rational approximation. At the beginning, when I came to Australia this time, Julian proposed me to work on approximation. Julian and Nadia proposed to work on approximation, rational approximation, and try to develop an algorithm, a projection algorithms to solve these kind of problems. And that's what we are starting to do. This work is not finished yet. It is still some points that we need to finish it, but it is almost complete. This work is jointly with Nadia and Julian. Julian is from Deakin as me, and Nadia is from Swinburne University. Okay. This is the outline. We will present an introduction. I will present the variation inequality, some preliminaries, some notations. After that, we will present the algorithms and the conversion from the algorithms. I will make an introduction to approximation theory, or a little bit just the definition and so on. And I will present some numerical experiments with two kinds of functions to approximate a continuous function. Okay? Well, I think it's better to do it here. Okay, in this work, Rn defined the Euclidean finite dimensional Euclidean space with the inner product, the induced normal by this inner product, the absolute value, just with one line. Conv D is remaining to the convex hull of the set D. Line D is the linear span of the set D. The graph is the graph of the operator T. In this case, this operator will be a point to set operator. And the graph is all the points in Rn times Rn, such that the second coordinates belong to T of the first coordinates. Okay. By this graphical Pn, we will denote the set of polynomial with degree n, and by this f or graphical f, we will define like an extension of polynomials. That is, we will take a linear combination of n function or n plus one functions when all of them are just functions, and when you take, for example, hi of t equal to t with power I, we recover fn becomes in Pn, okay? Then it will be the set of polynomials with degree less or equal to n. Okay, this is the notation, and let's start presenting the classical or variation inequality problem. These problems consist to find a point in the set C. Generally, this set is considered convex and closed, but not necessarily. Sorry. And the idea is to find a point on this set such that there exists an U star belonging to T star, that is X star, U star belong to the graph of T, such that this inequality be satisfied for all X on C. As we know, we denote the solution set for this problem as S star, okay? As we know, this problem, when you solve this problem, this problem is very related with the optimization problem. And we will see it later see the relationship between this and the optimization problem. When you have an optimization problem, if you take the subdifferential or the derivative of the functions, you will see that this problem with taking T as a differential of the function of the class or the class differential of the function, then these two problems are equivalent. Now, related with this problem, we have the dual variational inequality problem. That this consists a little bit different. Consists to find a point on C such that for all X and U on the graph of T, we have that this inequality is satisfied for all X on C. Okay, this X must be on C. Okay, and the solution set for this problem will be denoted by S0. Okay, there are some results on an example for which S0 and S star are not equals. Okay, but when the operator T is pseudo-monotone and it satisfies some kind of continuity, for example, the closed graph, then it is known that both problems have the same solution. There are equivalents when T is pseudo-monotone. But there exists a sample, can see in this paper, it will be presented on the bibliography, that these two sets are not the same. Okay, there exist operators for which these two sets are not equals, even when both of them are not empty. Okay. Okay, good. The definition, as we will present projection algorithms, we will need to talk about which is the projection onto the set C. It's the solution for this problem is with the nearest point of X on C. This will be denoted by the projection on C of X. Okay, this is classical, nothing new. And this is two results that we will use on the paper. And there are two classical properties also. Okay, there is nothing new in these two properties. Now, the most of the projection algorithms, not all of them, but a big part of the projection algorithms, they use the fact that the sequence generated by the algorithms, it is Fourier convergent. And Fourier convergent to the set S means that there exists a point, or sorry, there exists a subindices on the natural numbers such that this inequality is satisfied for all k greater or equal than these points. Okay, and is Fourier convergent to the set S when that's happened for all X on S. Okay, this is also a classical definition, and we will use this definition in the proof of the convergence of the algorithm, because our sequence will be a Fourier convergence sequence. Some facts in Fourier convergence is then when the sequence is Fourier conversion to a set S, then this sequence will be bounded. The sequence will satisfy this condition that for any points on S, this sequence will be convergence. And as we are working on finite dimensional spaces, it is enough to one accumulation points belongs to the set for which this sequence be Fourier convergence related to the set. If we have that the sequence contain only one cluster point, then the sequence will be convergent. The whole sequence will be convergent for these points. In infinite dimensional spaces, we need a little bit more. We will need that all the cluster points belong to S. But in finite dimensional, that is our case, it is necessary that only one point belong to S, okay? Okay. I said something about pseudo-monotone operator, and I would like to define what is a monotone operator. When you take any two points on the graph of T, you will have this inequality. Pseudo-monotone operator, when you take 2 points on the graph of T, this inequality implies the second one. And quasi-monotone operators will be that this strict inequality implies this second inequality. There are classical definitions also, and all of them are in point to set operator, but it is still true when the operator is not point to set, it's just point to point operator, okay? Now, it is clear also that this, every monotone operator is a pseudo-monotone operator, and every pseudo-monotone operator is a quasi-monotone operator, okay? Good. Let's present now the algorithms. First, for the algorithms, we will need a line search. And this line search is a modification that Lancer used, the line search F used in this paper. That is the same that I told before, and it will be presented at the end of the talk. And the modification we do was that in that paper, we only take any points U on T of X, and if that doesn't happen for all, but that is equivalent, is for all guys here, this is strictly less than this guy, then we increase these points and multiplying by alpha here. But the change that we need to do here is that this must happen for all U on T of X. Then we need that this inequality happens for any U in T of X here and for all U alpha in T of X alpha, okay, in T of X alpha. That means before is the same that you say that for all guys on T of X alpha, this happens, okay? Why we need to do this, this modification? Because the operator in the paper of Burashik and me, we asked for the operator to be an inner semi-continuous, because we are asking for continuity of the operator. But in this case, we will not need that the operator be continuous. In fact, because the problem that was the inspiration for do these algorithms, the operator is not continuous. Okay, as the guy is not continuous, then we cannot ask for continuity. And the way to avoid the continuity of the operator was increase more peoples here. Of course, this line share will be very, very hard to check when the operator, for any operator, because you need to make this problem a lot of time in each iteration. But that happened in the problem that we will apply these algorithms is that this line share will become very, very easy to check, and we will see it later. Okay, then we prove it that this line search is well defined, then it will stop in the finite many of steps, and the algorithm is as follows. Given that sequence below, bounded by below and up is finite number b hatch, and this b is far from 0, then we, for the numerical experiments, we take this beta k as 1, okay, for all k. And given the points on xk, then with u in t of x, that u in t of xk, uk, it will be the guys that satisfies these conditions, okay? Because when this line search stops, we will have this inequality with u in t of x and u alpha in t of this guy, in t of x alpha, okay? Then, given the point xk, we compute the point alpha k and u alpha k, and like the output of the line search, okay? Now the stopping criteria is very classical. If these two guys, xk and zk, coincide, then xk is solution. And also if sk is equal to this guy for any vk in t of xk, okay? These two conditions means that xk is the solution of the variational inequality. Okay, now we define a alpha bar xk like this convex combination, because this convex combination is exactly that we have here. That means that this guy is x alpha in the line search, okay? And we define the next iterate as that capital F or graphical F on xk. Who is this f case? In the next slide we will see it. There are two different ways to compute these iterates, okay? Again, if sk plus 1 is equal to sk, we are in the solution sets, and we will see later on why, okay? Now, how compute that f? It will be two variants. The first variant, we will compute sk plus 1, projecting xk on this hyperplane is defined in 6. This is the first variant, project first in the hyperplane, and after that we project on C. And in the second variant, we will project directly in the intersection of C and the hyperplane. This set is a small set than these two sets, but maybe it's a little bit more complicated to project, to compute the projection, because this projection here is easy to compute, because it is a closed formula. That doesn't happen here, okay? But who is this hyperplane? This hyperplane is a hyperplane that separates the point xk and the solution set, okay? Then you take sk, see the solution set, and you compute the hyperplane that separates strictly the point and the solution set. And we will see later that if you cannot separate the point and the solution, that means that your point is in the solution set. And we will see it later. Okay, which assumption we need to ask to our operator in view that we have conversions? And as we say later, the operator will not necessarily be a continuous. We only need that the operator be closed, which is closed that the graph is closed, okay? We only need that the operator be closed. In other words, this is altered semi-continuous. Altered semi-continuous is the equivalent with a closed graph. Also, the second assumption is that T must be bounded and unbounded set, but this is a classical, I don't know any any algorithms that does not ask for this assumption, because if you don't have this, you cannot control the guys on T of X. Then it is impossible to choose any of them, and you ensure that this guy be bounded. Then we need to ask for bounded and bounded set, but it's not complicated to be satisfied. It is classical but easy and smooth assumption. And the first assumption, that is the kind of monotonicity, but it's not monotonicity. We don't ask for pseudo-monotone, we don't ask for monotone. We only need that the solution set of the primal and dual problem coincide, or that the two problems be equivalent, okay? And solve one of them, you are solving both. And that is that we asking for. Of course, if the operator is pseudo-monotone and it satisfies A1, then it will be satisfied A3 automatically. Then pseudo-monotone operators and closedness of the graph will imply that A3 is satisfied, and we don't have too much problem with this assumption. Of course, as I said before, there exists some operators for which these solution sets are not the same, even when most of them are not empty. Okay, good. With these assumptions, if we start in a point that is not the solution of the problem one, that in theory, as we asking for A3 is the same that problem two, the variational quality, the primal and the dual one, then if we are not in the solution set, then the line search terminate after many finite iteration. The line search is well defined. It will stop in a finite number of iterations, okay? Of course, that is why we need to ask if the current point is in the solution set or not. The second proposition is that I told you, if you cannot separate the point and the if the hyperplane cannot separate X from the current point from the solution set, is because you are in the solution set. That is why that Sk is in the solution set if and only if Sk belong to Hk. Okay, if you cannot separate it, is because this belongs to the solution set. Okay. Now, of course, if the algorithms stop in the finite number of iterations, we will be in the solution set, and this proposition will ensure it to us. Why? Because each time that the algorithms stop in a finite number of iterations will happen, or the first one, the projection, that we will use the first fact on the projection step, and the second fact, or we will use that is the algorithms stop is because Xk belong to Hk. Okay, and this proposition basically will ensure that the algorithms, if they stop in a finite number of steps, then it is stop in the solution set. Good. Now, using the fact that that we are in the projection kinds algorithms, we will have the Fourier conversion to the solution set. That, remember, A3 will ensure us that this guy is also equal to S0, then it is Fourier conversion also to S0. And this is the point of the proof of the convergence. And that is why we asking for S0 be equal to S star, because we will prove that the sequence is Fourier convergent to S star, that is equal to S0, then that is why Xk is a bounded set, is a bounded sequence, and we will prove this important limit inequality that will give us this limit is equal to 0, and this item 3 will give us the main idea for the proof of the convergence of the whole sequence. that three properties is satisfied by both of the variants, okay, for all variant 1 and variant 2. And of course, when we have this property, then we will use the fact that Sk is a convex combination of this guy and set k, and then it will appear here an alpha k go to the front, and we divide the idea, we divide in two cases, when alpha k goes to 0 and when alpha k does not go to 0. Then we take in a subsequence and we prove that this subsequence will be convergent to the solution set. This is the idea for the proof. Of course, I will not do here because of the time. For the variant 2, we will have that Xk plus 1 that is equal to this guy, it will be equal to this guy. We can project first on Hk, and after that project on this intersection of sets. And this kind of compute Xk plus 1 will give us the same properties, not the same, but almost the same properties that we will use together with that the limit of the next iteration go to 0. These two properties combined with 3 with proof that the second variant also converge to the solution set, and this is the next theorem. Both sequence generated by both variants, they are convergent to a point in the solution set. Okay, and this is the proof, and this is how we proved the convergence of both sequences to the solution set. Then the algorithm works. It generates a conversion sequence. Then we are able now to try to apply these algorithms for solve our problems. Consider approximation of continuous function. Consider a function f continue and the compact set I. This compact set can be an interval or not. It can be just any compact set. Okay, the only that we ask for compactness is because we need that this sub here, it have a point on T that satisfies I don't know how can I say that these points be realized. You can find a point for which this sub is equal to the function evaluating on these points. Okay, then we are interested in approximate f by rational functions. Look, in this point, we are not asking that this rational function be polynomials. They can be any kind of approximation, and this is a very good point because we can approximate f with the function that we want. It can be good if you have an idea of how f is, in case that you don't have exactly who is f, and so on. Thinking in application to other kind of problems. Of course, when the p and q are polynomials, they are included on f more than f in p, okay? And then we need to minimize in p and q the maximal deviation function, okay? The maximal deviation function is the supremum in as I is a compact set, we can substitute sub by maximum. It's not a problem, okay? Because the maximum will be realizing in a point. And this is a problem of a rational approximation. Take a function and try to approximate by rational function. Rationals not in the sense of polynomial, but just on a function and another. Look that you don't need, not necessarily p and q must be the same kind of function. For example, p can be a polynomials and q can be polynomials. Instead of t, you can have a sine of t or something. Okay, then it's not necessary to be the same kind of function both in the top and the bottom. Good. The notation of P will be this guy when A is equal to this guy in Rn plus 1, and B is equal to B0, B1, and Bn. Okay. Of course, the degree of the guys on the top not necessarily must be equal to the degree of the guys on the bottom. The only that we need is that P and Q are real functions. Good. Okay, this problem can be written in this way when phi is the maximal deviation function. Okay, and as the set C, in our case, we will use that the guys in the bottom be greater or equal to 1. Why? Because we need to avoid that this guy be 0 because it will not approximate it. And in terms of projection algorithms, we will need this convex set, okay? And we will also, when you multiply A and B by the same point, by the same real number, you will have the same solution. Then it is not we don't lose any solution, assuming that the polynomial or the function in the bottom be greater or equal to 1. Okay, for all t on I. Again, if you choose pi of t and qi of t as t of I, then problem 7 and 8 becomes in the classical rational approximation of continuous functions, when you have to approximate a function by the polynomial over another polynomial. Okay. Now we denote the sets A plus and A less and A minus by the active values set, and it will be A plus the t on I, such that this function will be equal to this function, and A minus by the t for which this guy is minus this function. Of course, this will be this active point, and this point will give us the point in which this function realize the maximum or the minimum in this. The minimum, of course, the maximum, but the minimum if you remove the brackets. Okay. Okay, good. This lemma is very known in the theory of rational approximation, that this function is quasi-convex function. This function is a quasi-convex function. The idea of the proof is because for any t, fix a t on I, then this function is quasi-linear, then the supremum of quasi-linear function is a the quasi-convex function is quasi-convex. If this guy is quasi-linear, then it is quasi-convex, okay? And then this proof this lemma, okay? Good. Now, in the books of Rockefeller and Wetz, analysis, I don't remember the name of the books, they prove that the Clark's differential of this function is equal to the convex combination of all the derivative or the gradient of the function, this function, okay? But computed in the active points. When the point is active in A plus, then we will take the positive gradient, and when the guy is on the A minus, we will take the minus of gradient. And when you take the convex combination of all of these points, then you will get the Clark's differential. Of course, the majority of the time you will have here a finite number of points, because if you have infinite number of points, in some sense, the function that you want to approximate in this part in which you have a finite number of points, it's like a rational function, and then will not be so interesting to approximate. Then in the practice, all of these points, not all, but in the practice, the great majority of these points here will be a finite number of points, and then we are taking the convex combination of them. And this will give us a way to compute or to implement the line search. That line search that I told you that is very difficult to compute. Good. A proposition, the next proposition is that if 0 belongs to the Clark differential of the point, then this point is a Goal minimizer of phi. And this is a very good point because it will give us, together with this theorem, that this function is a pseudo-monotone, is a pseudo-convex function. Okay, the function phi, it is a pseudo-convex function, and this is a new result. As we know, the function that the idea that people have is that this function is only a quasi-convex, and we prove it that this is more than quasi-convex, it is pseudo-convex function. Consequently, the Clark differential is a pseudo-monotone operator. And as the Clark differential is a pseudo-monotone operator, we can apply our algorithms. And that is what we're going to do. We will apply the algorithms in view to see what happens when these algorithms try to solve the problem of find a polynomials or something more general than the polynomials over and down to approximate the continuous functions. Some facts. This guy is pseudo-monotone, then taking t as this guy, as the Clark differential of phi of f, we have that the problem S0 is equal to S star, then this operator satisfies A3. It is not difficult to see that it satisfies A1. It is also, I didn't put here, but it will be good to put, that we proved that this operator have a closed graph. It is not too difficult to see because the way it is defined in the classical, the Clark differential. On EI2 also is not complicated by the continuity of the function f and the continuity of the function phi on the set C, okay? Because the set C is that the polynomial down, the minimum value that they attain is greater or equal to 1. Okay, now as well know that problem 8, the minimize the function phi is equivalent with the problem 1, the variational inequality, when you take the operator like the Clark differential, was mentioned before. Then solve the problem 8, it is enough to solve a problem 1. But what happened when we want to implement the line search f? What happened with this line search? Because it's very difficult to compute the whole points on the set T of xk. But it is not because the way that we compute the Clark differential. This is line search, transform it and apply it to our problem. AB is the point X on C. Then if for all guys on this set, we don't need to take the convex rule because as the Clark differential is the convex rule of all of these points, if this inequality is satisfied only in the point that generated sets, then as you can see here also, we compute the minimum of this set on d alpha, and the alpha are only the points that generate the Clark differential. Then we don't need to ask for all the points on on T of xk, because we have the T of xk in our cases are the convex combination of some points. And in a practice, this will be a finite number of points, okay? Then the line search will not be so difficult They just need to compute some a pure points, a few kind of points, and try to solve the problem. If not, then you increase alpha and go to again make the process again. Okay, and our output of course will be the guy from T of X alpha, this guy, and alpha. Okay, that this is the line search in the case of our problem. The algorithm will be the same. It's not change anything. Just change xk by ak and bk. Okay, good. Now, the first part of the algorithm of the numerical experiments is dedicated to polynomials approximation. We take one polynomial over and polynomial down. Degree n open in the top and degree n on the bottom. For the first case, we take as I the whole interval minus 1, 1, and we run 200 iterations. And in these 200 iterations, we extract the best result for each variant. Okay? Ether is the number of iterations, and an m represents the degree of the polynomials in the numerator and the denominator respectively. And the pictures, the blue color is for variant 1, the red color is for variant 2, and the green color is for the graph of the function that we want to approximate. Good. This is the numerical result. We tested as the function that we want to approximate these four functions, absolute value of t, sine of t, absolute value of sine of t, and the square root of the absolute value of t. For this function, just this one is smooth, and that is why I have the better results, and all of them are not smooth functions. Then the algorithms is, of course, the solution set is not exactly the zero, or is more complicated to approximate. And we see here that in most of the cases, the first algorithms obtain better results. Not in all, but almost in all. Here is better the value of the function. This is the function value on the better point with strictly less than 200 iterations. And both algorithms have very similar behavior, but I think that the first algorithms or first variants in some points, not on this kind, that are very competitive one to the another one. And there are some pictures. As we can see, we have this guy as the only active point, because here is not in the top. Here we have this guy as the active point. All of these guys down are when the functions coincide with the rational approximation. Here, most of variants have similar or almost the same behavior, but doesn't happen here. Here is the function absolute value of t in green, and the two approximation. These functions are p, like here, f and p over q. Okay, and here is the again the function that we want to minimize. Okay, the maximal deviation function. Okay, the same for sine of t. Of course, both algorithms have very similar behavior, and they both approximate very well the function sine of t. Here is absolute value sine of t that is not continuous on zero, and this is the approximation of the function. This is the objective function. Again, with this is a point the active set, and this is the active set for the case of the red function. And for a square root that is most incisive here, this point here is very hard to approximate by continuous functions. And this is the result, and this is some pictures. But in this section now, we know the solution set. In these cases, in all of these cases, we don't know which is the solution set. Even today, we don't know who is the solution set. But in these cases, we know who is the solution set because we will approximate some rational functions. And we will take some rational function and apply the algorithm to see what's happened. In all of the cases, we compute the distance of the current point to the solution set. We stop the algorithm when the function, the maximal deviation function, is strictly less than 10 with power -3, because we know that the solution will be 0, and the compact set will not be the whole interval. It will be some points, equidistant points in the interval. Then we choose some points in the interior, in the interval -1, 1 as the compact set, okay? And the results are in this table. This is from the first variant, and this is for the second variant. And as we can see, in all of the cases, except the first one, the second variant was better. Too much better, I think. In some cases, less than the half of the number of iterations. And the results also are very, very good for the second algorithms. Remember, this is the distance to the solution set, and this is the number of iterations. Here we tested different degree for the polynomials, and this is the function we tested. The constant function, 1 over t squared plus 1, t over t plus 1.5. All of these functions are continuous on the interval, otherwise we cannot approximate it. And as n, we choose 100 or 200 points in the interval, okay? Now we tested the algorithm for non-polynomials approximations. We take not polynomials and approximate the function for see what happens. On this case, we compute the CPU time for see how fast or how much time the algorithms spend to solve the problem. AHT will denote the function for we compose the rational function. Then all the rational function will be a polynomial, but instead of t, we put h of t, okay? It is not a polynomial. We are using h of t as in the place of t in the polynomial. Then the function will be 1, h of t, h squared of t, h cubed of t, and so on. Okay, again, now we take this function to approximate. This will be the only function that we want to approximate in this case. Again, we take equidistant points in between -1 and 1, and we stop it when the function, the maximal deviation function is strictly less than less or equal to 10 to -2. Why we choose this function? Because we realize that the algorithms obtain this precision to the function that we want to approximate this function. Okay, and the results are on this table. Again, this is for the first variant, and this is for the second variant. The first case, we took the function h by e of t, the exponential of t, and we tested several degrees from the top and the bottom, and several quantity of points, and the numerical results see that, of course, when you choose the degree is bigger, then they will spend more time and more iteration in both those cases. And the second function we used was instead of e of t, sine of t, with the same degrees and the same quantity of points, and the result was too much better from that function is too much better approximated by polynomials with sine of t than with e of t. Of course, the function has sine of t in this composition, but it's not strictly sine of t. Then this was the results, and the conclusion: we made an algorithm, new algorithms. As far as we know, there are not exist another algorithms in the literature, as far as we know, that solve this problem, pseudo-monotone and point to set operator, but more than pseudo-monotone that S0 is be equal to S star without continuity and without monotonicity. The Claxo differential of the maximal derivation function is a pseudo-monotone operator. This is a new result also. And we provide an application to rational approximation. As some open problems, we can extend this algorithm to infinite dimensional spaces. Talking about just the algorithm, I don't know the approximation function in infinite dimension. I don't think that this has made so much sense. And can we find a full implementable line search? Because this line search is implementable by the phase of the Claxo differential of our problem, of the approximation problem. But if we have not the phase of the, if you cannot, if you don't have an operator that is so easy, what's happened? And also, can we extend this kind of algorithms for other approximation problem, piecewise polynomials, for example, piecewise rational approximation? This can be also do. Okay, this is the reference. This is the paper from Regina in Brazil. For we use the line search. This paper we use the algorithm in some way because the algorithms are very similar. This is the paper we are working on. It is in preparation yet. And this paper gives us some result on pseudo-monotone and pseudo-convex and quasi-convex functions. Okay, thank you very much.
Thank you, Reinier, for your presentation.
Thank you.
And while people in the audience are thinking about your open problems, can I make a small remark? When you computed the Clark subdifferential of the function psi, you referred to the book by Rockefeller and Wetz.
Yeah.
And you said that you didn't remember the title of that book.
Yeah, I have it.
I just want to say that at our seminar on variational analysis and optimization, it's not allowed to forget the title of that famous book. Because it's called variational analysis.
It's variational analysis. That is the number of I forgot at the time, at this time.
I believe now you will remember the title forever, as well as everybody in the audience.
Yeah, good.
Do we have questions? Please. Regina?
No.
Okay. No. I see that your microphone is on. I thought that you were going to ask a question. There was actually a comment in the chat, terminological comment from Wilfredo.
I cannot see the chat. How?
Oh,
can I
you
do
can't? Oh, just click on the chat.
Okay. I'm fine.
While you are looking how to click on the chat, it is actually about you can see it, right?
Yeah, I can see it. Yeah, Wilfred, this is the Stampakian problem, and the second is the Minty problem. Yeah, the Minty variational inequality or the Stampakian variational inequality. That's correct.
So, now you know the title of the book by Rockefeller and Wentz, and you also know the names of Stampakia.
Yeah.
So I keep entertaining the audience, waiting for questions. Questions, please.
Maybe I do have one question. You said that you need the two sets, S star and S0, to be the same set. but wouldn't only one inclusion be enough?
No, because sometimes we, the majority that's happened is that S star belongs to S0. And as we have, that will give us the continuity or the closure graph. And as we have that the set, that the sequence is Fourier conversion to S0, we need to ensure that all these points belong to the set S star. And that is what we ask for the equality.
And just another question. If in the algorithm, instead of having the projection over that intermediate hyperplane, H, that separates the current iterate from the solution set, could a projection to some other closed and convex set that separates also give you convergence? So instead of having a hyperplane, maybe you have another closed and convex set that contains the solution set and it's separated from the...
If any subset, any set that satisfies these conditions here, it will work.
Okay.
This condition must be satisfied. If you cannot separate, it's because you are in the solution set. And what you know that you cannot separate because you are in the solution or SK belongs to this set. Any set that satisfies this condition will work for sure.
Okay. Okay, thank you. So those are all my questions.
Thank you for your question.
More questions, please? Comments? Criticism?
Criticism. Yeah, that's good. Criticism is very good.
But what about the absence of criticism? It's probably also good.
Maybe,
Exactly.
sorry, maybe, can I ask another question?
Go ahead.
What you do in the approximation by rational functions, you calculate, essentially you do a projection using the infinity norm.
Yeah,
right?
the distance norm.
You're using a projection using the infinity norm, right?
Yeah, the classical is, we are in Rn. Yeah,
yeah, that's the classical analysis.
Yeah.
It's a classical analysis of interpolation. When the idea of norm is the infinity norm, that's why you need a compact set, capital I.
Yes, here, yeah.
Yes, oh, yes.
Not,
if you don't take the infinity norm, but you take the norm 2, for example.
Yeah, it will be another problem. Just, you mean in this point?
Yes, exactly. In 7, you take the minimum of the infinity norm of f minus a set of rational functions.
Yeah.
So that's the norm infinity.
But in approximation theory, this guy f of t is a real number, and this guy is also a real number. It is not vector here.
Yes, but you are. This is the infinity norm distance. So you are projecting f using the infinity norm onto, let's say, is it the subspace, the P over Q, right? So you are in equation 7. In equation 7, that's the minimum of the that supremum that you have there is the infinity norm of the difference of f minus pi over q, minus p over q, right? And you are computing this for every p and q in those sets.
Yeah.
So what you are doing is you are doing a projection of the function f with respect to the infinity norm.
This supreme is on t.
I know it's in t, but you understand what I say? This is the minimum for every p and q.
Okay.
of the infinity norm. The infinity norm is the supremum for t in I of the differences that you have there in the absolute value.
Because Regina, what I understand, if I'm understanding why your your question, is that this is an infinite norm. But the problem is this is a real number.
No, but I'm not saying that the norm is infinite. I'm not. You know that the LP norm, the LP for p equal infinity, is the supremum for t.
Yes, yeah, but this is when you have a vector. You don't have a vector here. This is a real number. P of t is a real number, and Q of t also is a real number.
Yes, but just wanted to say, if you have two continuous functions defined in a compact set, you can define the distance between those two functions. And the distance is, the infinity distance between those two functions is the supremum.
Yes, it's this one. Okay. Yeah, I understand your point. Okay. It would be another problem. It's good to thinking on this kind of problem. I don't know if Julian have some application to this kind of other kind of approximation, but this is a good point, I think.
Well,
I understand your point. You take another norm here, approximate f by another kind of approximation, not
exactly.
the
yes.
Yeah, I don't know.
For example, you have I don't know. There are many types of approximation of functions that are used for construction of roads. For example, they use L2 approximations of functions. So you can use a different norm there. And what would your function psi look like? And what would your approximations look like when you change the norm?
Yeah, legitimate question. There is something to speak about.
The most difficult thing will be compute the subdifferential, the class differential in this case.
Can be even simpler.
Maybe will be simplest. Yeah.
Maybe help Reinier a little bit.
Okay, so good, thank you.
Yes, so actually, yes, of course, it's really very important which norm you use, because it actually may be more suitable for a particular application, for example. So I believe for us, it's probably more a kind of historical answer. So we became interested in Chebyshev approximation, which is uniform approximation. So that's why we use this norm. So, but definitely you can use other types of norms. And many people actually prefer least squares, although it's not a norm, but it basically leads to simpler optimization problems. But we somehow like this one. Let's say.
But in this case, it's not simpler.
In this case, yes, that's right. In the case of rational approximation, I wouldn't actually say that least squares is simpler, because sum of quasi-convex functions is not necessarily quasi-convex. So, and that actually makes it not so easy to work with least squares, because here we have summation, right? So, but for uniform norm, because you take maximum, and maximum of quasi-convex functions is a quasi-convex function, so we are still within the nice class of functions which are in a way manageable. Yeah. So that's what we are doing. But if it's not a rational approximation, but some kind of polynomial approximation, piecewise polynomial, then these squares are actually simpler.
Okay, thank you.
It can be nice to have a differentiable norm. This is also an advantage. And there is actually a question in the chat about using Clark subdifferential, and hopefully Reinier will answer this question. But I just want to say that if the norm is differentiable, you indeed don't need Clark subdifferential. It will be probably something simpler. But anyway, Reinier, can you see the chat?
Yeah,
there's a question from Evgeny Nurmitsky. Can you?
Yeah.
You're reading, okay.
Yeah. Do you really need Clark subdifferential for such relative simple functions?
Oh,
The problem is the function is not as simple as appear because they are not differentiable. We'll not see one or semi-smooth function with there. So differential being, I don't know, maybe the second question will be C11 or semi-smooth function be with their subdifferential being out. I don't know, maybe it's, but the problem as we formulated, then the class subdifferential is the most adequate that we found. Maybe another, but the problem is if this other subdifferential satisfies that the solution of the variation inequality solve the problem of minimization is welcome.
the thing is, I think that to complete that is that the Clarkson differential is actually quite simple in that case.
Exactly.
The function, I agree with Reinier that the function itself is not particularly, not as simple as it looks. It's a bit deceptive, but the Clarkson differential is, we have an explicit formulation for it. So that's one of the reasons we're using it.
Exactly, and they allow us to be implementable the line search, because this is a problem. This line search is a problem. When you don't have a structure on this on the T, then will be a problem to solve this problem each time that you make it in each iteration. This problem must be solved sometimes many times.
So it's not that we chose the Clarkson differential, it's the Clarkson differential chose us in this case.
Exactly.
Okay, maybe another subdifferential is in line to choose you to do something about it. But by the way, you wrote this formula for the Clark subdifferential. It involves this convex hull. Mm-hmm. And what if you remove this convex hull? Maybe your life will get simpler.
We only work, exactly.
And this is, by the way, this is another comment. This is basically what Evgeny Nurminsky was doing many years ago. So take this question seriously, please. And as far as I can remember, it did make sense from the computational point of view, at least for those problems which they considered at that time in Kiev. Another question from Evgeny?
Yeah, not always this T always separated, but in the practice, when you will use the algorithm, it is only a few points, because you should have.
Okay.
Yes.
And Evgeny wants to add something to his question. Can you actually speak? Is your microphone already working, Evgeny? No. Okay. So you have an addition. How can we see your addition? How can we get your addition? In mail? It's coming. Probably Evgeny is writing now. Any more questions, comments while we're waiting for the addition to arrive? So I'm not sure whether Reinier can immediately comment on that. You might actually have some correspondence, Evgeny.
The question was asked and answered, so question is sealed. Was already answered by Nadia in the chat.
Yeah.
Okay, but there was some addition. There was supposed to be some addition to that question. Anyway, any more questions, comments? So let us get together to thank the speaker, Reinier. Thank you for your nice presentation.
Thank you, Reinier. Thank you, everyone. Thank you.
And apart from interesting talk, it was almost perfect timing. If not for the last series of questions, we would even finish by 6 o'clock, but it didn't happen.
Okay.
Thank you, everybody.
Okay, thank you, everyone.
See you next week.
Bye-bye.
See you. Bye-bye.
See you next
Bring
week.
friends,
Bye-bye.
family, and let's
Thank you.
get together in a week. Bye-bye.
Bye-bye, Reinier. Thank you for the nice talk.
Bye-bye. Thank you for being here. Thank you very much.